Hey everyone, welcome to part 2 of one-way ANOVA within. In the first part we were defining what a one-way ANOVA does, which is look at 3 or more levels of an independent variable and compare them on the outcome or dependent variable to see if their means are different, to see if there is more variation across the groups than there is across the sample as a whole. So we were finishing up an example and looking at step 4 of hypothesis testing, where if we were trying to look at, say, different kinds of nacho chips, just to remind you of the example, to see if we had people try 3 different kinds, whether they would figure that they liked a certain brand or kind better. These data are made up, so with no love lost or slander to any particular chip type here, we are just seeing if there is one group that might be better than another. This was not an actual taste test. So if we have flavor ratings, perhaps scaled from 0 to 100 for each of the chip types, and we have people rate which one they like better, where a higher score means more flavor or better flavor, we ended up with an outcome, and we were looking at our F value, looking at the 2 levels of degrees of freedom that we would have across the groups, and calculating our F value, significance, and eta squared, which gives us a measure of the size of the effect. And so we could write up something like this. We could either put our descriptives in a sentence, or we could tell people to see a table for our descriptive statistics, and then tell them that our results here did indicate a large, based on the eta squared, significant, it wasn't that likely or probable, difference, our F value was big, in flavor rating by nacho chip types. So this is how it would look in APA format to have all those pieces included. Our F value, our degrees of freedom, the actual F value, the probability we calculated, and that eta squared, here represented as partial eta, but we've only got one independent variable, so the partial is identical to the regular squared, and we've got that effect size that shows a large difference. So if we were going to graph these results, we could use SPSS or a bar chart in Microsoft Word to show the difference and the standard error or the variability for each of these groups. And these captions and titles have been updated to APA 7th edition format that just came out in October 2019. And so we're done, right? We did find a significant F value. Well, the problem with an F value, if it's significant, is it only tells you that a difference exists somewhere. It doesn't actually tell you where those differences exist. So just like in a between subjects ANOVA, we're going to need to do a post-hoc test, an after the effect test, that helps us determine and describe where that difference exists, which pairs were different from each other. So that requires a post-hoc comparison. So this is a little bit more about effect size, if you haven't covered that before, and to tell you a little bit about how we tell which pairs were different within that ANOVA. So first off, a little bit about magnitude of effect. ANOVA tells us whether the factor we're looking at has a large effect or a different size using eta squared or partial eta squared. And a full eta would be if we just had one factor. A partial eta would be if we had several independent variables and we were looking at main or interaction effects, if you're familiar with factorial ANOVA. So it takes the sum of squares between divided by the sum of squares total, not here influenced by sample size, to figure out that effect size. In other words, we're looking for the proportion of total variance accounted for by the independent variable and not the total variance possible across the sample. If you are looking for a way to determine how large an effect is for eta squared or partial eta squared, some researchers have suggested a small effect is 0.01, medium effect 0.06, and large at 0.14. So that helps you translate math to English. So a post-hoc test, again, is calculating how far apart the means for each pair within the levels of our independent variable are. So if we have 3 levels, A, B, and C, or 3 types of chips, how does the first type compare to the second, the first to the third, and the second to the third? So we want to set an overall alpha level either at 0.05 or 0.01 in order to help us figure out how far of a difference we need to have for each pair for it to be significant. And there are several possibilities when you look at SPSS of outcomes that you can do. We would have our least significant difference, or LSD possibility. Most journal articles and statisticians like a Bonferroni correction because it's a little more conservative and it makes us less likely to make a type 1 error when we're doing multiple comparisons here. So it is like a t-test for each pair, but they're all run together, again, to minimize the possibility for a type 1 error. If you are doing Bonferroni corrections for post-hoc testing, you can take that overall alpha level, and you can do this with between subjects as well as within, and divide it by the number of comparisons you're making to be even more rigorous about how significant something needs to be before we call it different. So this helps, again, reduce that likelihood of type 1 errors and keeps publishing statisticians happy about being a little bit more conservative with our data. So when we run our ANOVA, which we can do through general linear model, and I've got a separate video for how to run that ANOVA if you want the SPSS help, what we're going to end up doing is look at each pair of the levels in our independent variable to see if that pair is significant. In this particular made-up example about 3 different types of nacho chips, only one of those pairs was significant. The Mission chips had a higher rating than the Kroger chips, but the Mission and Tostito chips were not significantly different from each other, and the Tostitos and the Kroger chips were not different from each other. So Kroger to Mission chips was the only one that was different, again, with Mission chips having a higher rating. So you would need to go back, and in addition to what we had before right here in the first half, we would need to include a sentence that tells people which post-hoc test we used. And if you're in a stats class, your professor might ask you to explain why you picked that versus the other post-hoc tests you could do, but at least say which one you used, and then tell which pairs was significantly different. So in this case, we found out that the Mission branded chips received a higher flavor rating than Kroger, but not Tostitos, and Kroger and Tostitos did not differ from each other. So we might put a star or mark between the first group and the third one, and then we didn't have stars between the other groups. One last thing to know about post-hoc comparisons is that there is an alternative. If you, before you start your data, have a way to weight or compare certain pairs versus others, you can do what's called a priori, or planned comparisons, where you can not only compare one group to the other, but you could compare a batch of groups to something. So this would be used in a place where your logic suggests certain comparisons should be made before you do it. You can also conduct comparisons, again, afterwards, but this is a way to set up which comparisons that you want to look at, whether or not your overall alpha is significant. So you will most often see a priori comparisons when you get a little further along in statistics, and you might be able to see if some combination of groups might expect similarly, and contrast those to others. So maybe you had 5 conditions, and you expect the first 2 conditions to be better than the last 3. So you can compare these 2 groups to those 3 groups. Look at other resources for more on a priori comparisons. I just wanted to mention them here for my stat students because sometimes articles will talk about a priori or planned comparisons instead of just comparing each pair. So I wanted to make sure that you knew that that was an alternative. This concludes our sessions on one-way ANOVA within, and I hope it helps you make sense of how to compare an independent variable with 3 groups on a dependent variable that is continuous. Thank you.